So, okay. Last time we were here, Monday, yay, today, awesome. We're talking about buffers. Buffers, of course, is a solution that resists changes in pH. So we're not saying that the pH doesn't change, and we actually haven't even got to the part where we see how much it does change. That's the first thing on our list of things to examine today. But nevertheless, this buffer is a solution that resists changes in pH. When you add a small amount of an acid or a base, then the pH will change, but not by as much as it could. So what I mean by that is if you add a small amount of acid or base, a strong acid or a strong base, to pure water, the pH goes very far, very quickly. If you stop and think about it, we kind of know that already. We determined the pH of a 0.1 molar hydrochloric acid solution. So people at least you know how to do that. Okay? So the pH of a 0.1 molar hydrochloric acid solution, you know the pH of that is 1. Then if we have a 0.1 molar hydrochloric acid solution, you know that's a strong acid. And 0.1 molar means 10 to the minus 1 molar. And if it's 0.1 molar acid, it's 0.1 molar hydronium. And if it's 10 to the minus 1 molar hydronium, because that's a strong acid, then we know that the pH for that is 1. Now if you take that same amount of acid and put that into a buffer, the pH would not go as far. Because, let's see, back story up just one more time. Absolutely pure water has what pH? 7. And yet when I put a 0.1 molar hydrochloric acid solution in there, it drops from 7 to 1. That's a 6 pH change, which you remember means 10 to the 6th difference. That's 1,000,000 times more hydronium than it had before. But if you do that same thing to a buffer, you will not get such a drastic change. You will not get a pH move of 6. So that's what buffers do. They resist changes in pH. How do you get a buffer? A buffer must consist of some weak acid and its conjugate base. So out of this potassium fluoride salt, it's only the fluoride part of it that's really the active component of this buffer. For the potassium fluoride, sodium fluoride, that doesn't matter. Okay? It's the potassium and sodium spectator ion. And again, as we discussed in the previous chapter, the pH is neutral. No impact on the pH. So if I take a weak acid and its conjugate base, or alternatively, occasionally we'll take a weak base and its conjugate acid, put those two together, then I get a buffer. A solution that resists changes in pH. And the way that it does this is any base that gets added to this mixture is going to react with the acid form, but it's going to change that acid form into the other component that's part of this mixture already. And so Chatelier's principle says, hey, there's going to be some shifting around in the equilibrium, but when it comes back to equilibrium, as it turns out, it's going to get back pretty close to where it was in the first place. Or any acid that I add to this is going to do the opposite. It's going to react with the base form of that. And the base form of that will then get changed into the acid form of that. So Chatelier's principle says that the equilibrium is going to shift, but when it's finished shifting, it gets back to equilibrium again, it's going to still have pretty much the same hydronium concentration. A little bit less than it had if I put a base in. A little bit more than it had if I put acid in. But not as much as if I put that acid or base in pure water. It has no buffering ability. So what we also did is then we that little bit about buffers, we then started doing some calculations and chemistry. We got plenty of math to apply in this course. And so what we did is we calculated, and that's really what this question is all about. What is the pH of a buffer? That is 0.14 molar hydrochloric acid, so the pKa is 3.15, and 0.071 molar potassium chloride. So what is the pH of this solution? We have two options. That's what we figured out the other day. We could go back to our regular ice diagrams, initial change, equilibrium. put in the two initial concentrations. Calculate the change, let X represent the change, and then figure from there and go through our typical thing, get the K value known, and solve for X, and determine pH that way. Or, for buffers, we have this Henderson-Hasselbalch. And if I know the K, or better yet, the pKa as shown here, then I've got a relatively simple formula that shows me how to do that. And in this particular example, that's what we did. There's the equilibrium that we want to investigate. And here is the Henderson-Hasselbalch equation. pH is pKa, and the conjugate base is on the top, and the corresponding acid is on the bottom. And you just plug in those two starting concentrations and the pKa, and you solve this relatively quickly for the pH. And so, right quick like, we've got a number for pH. If you prefer the ice diagram, you're welcome to it. Okay? So use that. Either one of these methods will work fine. Personally, I like the Henderson-Hasselbalch. Even if I'm given a Ka, for me it's quicker to take the Ka, turn it into a pKa, and then use this than it is for me to work myself through an ice diagram, an initial change in equilibrium. But it's totally up to you. You should always check it. I don't often do so because I go by my general rule of thumb that if the initial concentration and the K are at least 3 orders of magnitude different. Specifically, if the K is at least 3 orders of magnitude smaller than the initial concentration, that's 10 to the third difference, then my approximation is still invalid, and I don't bother checking it. If it's 10 to the third, then I might have to check it. If it's 10 to the second, that's not going to work, and I will have to actually use a quadratic analysis in an ice diagram. So, which one do I use? Do I use the full analysis, the initial change in equilibrium, the ice diagram, or do I use the Henderson-Hasselbalch? Well, it really keys on the Henderson-Hasselbalch is based on the X is small. If X is not small, then you can't use the Henderson-Hasselbalch anyway. For me personally, the Henderson-Hasselbalch is quicker and faster, simpler for me. Just remember down here at the bottom, that's my rule of thumb as well, that if it's 1,000 times 10 to the third, if Ka is at least 10 to the third smaller than initial concentration, we're good. And technically, I want to compare it to the acid's initial concentration. After all, it's the Ka, the acid equilibrium constant, that I'm working with. Any questions about those things, comments about those things? So I think that's where we stopped the other day. We started working some of this. Oh, we did. So, right, how much does the pH of a buffer change when an acid or base is added? And right, and what we talked about was stoichiometry was the first part of this. Once you do the stoichiometry, then you're right back to the equilibrium equations that we've been working with. And the Henderson-Hasselbalch equation, once again, can be used for step number 2 for the signs, or you can use an ice diagram for step 2. Whatever you are more comfortable with. Just remember that these things are a timed situation. So, the stoichiometry part, though. Stoichiometry is based on moles, not molarity, so that's most likely where you're going to get tripped up. Is thinking molarity is moles, and it's not. One more reminder for our contrived example that we used for class on Monday. We made our solution volume 1 liter, so it made the mole calculation much simpler. So mole and molarity works very nice and simply when the volume is a liter. But here's what we did. We looked first at stoichiometry. In this particular instance, we were adding a base. That's a strong base that's being added. A strong base is not really in equilibrium at all. A strong base is going to push the equilibrium completely to the other side. Strong acid, by the way, is going to do the same thing. They will push equilibrium fully to the other side because they have very large K values. So what I need to know is the number of moles, not molarity, and I'm going to try to keep saying this over and over and stressing it so that I hopefully can persuade you to make sure that you move to moles and don't simply use molarity. Of course, the question just counts in terms of moles. But if I add 0.01 moles of hydroxide to a weak acid, it is going to react with that weak acid and remove 0.01 moles of it. So once it has done its business, there will only be 0.09 moles of that weak acid left. But it changed the weak acid into its own conjugate base, so it's going to increase the conjugate base by the same amount. So it's going to 0.01 higher than the conjugate base was, 0.01 less than the weak acid was. Now that I have those new values, I need to change those moles into molarity. So there's one more line that's been added to our table. And we'll get down there to it. And here it is, right? So we know how to get molarity. It's moles divided by volume. So you must keep track of the volume of these solutions. They will become important for this first part of the calculation. Coincidentally, one more time, coincidentally, because we've chosen 1 liter volume, the math is simple. You divide by 1, you get the same number. But once I have those values, then I can go back to my ice diagram or my Henderson-Hasselbalch, whichever one I prefer. If you like ice diagrams, then use an ice diagram. Put all those values in there. Do your X is small assumption. Calculate the value for X. Once you have the value for X, then yeah, you should go check it. Make sure that it really is as small as you think it is. Or you can use the rule of thumb, right? X K compared to some of each. And then once you know the value for X, because X represents the hydronium concentration, then you just take the negative log of it and you get the pH, 4.83. Or alternatively, you can do the Henderson-Hasselbalch equation on that equilibrium. Choice is yours. So whichever way works for you. Henderson-Hasselbalch. There it is, 4.3. Again, I think that's a lot shorter than the ice diagram. Check your approximation, sure, why not? So that's where we stop. Comments, questions? Okay. So I keep saying that when you add this amount of base to the buffer, the pH changes, but not by as much as you might think. And by as much as you might think means really compared to pure water, which has no buffer system at all. And so, if I want to make a comparison, here on the left is the calculations that we did the other day. pKa for acetic acid is 4.75. You put that into the Henderson-Hasselbalch. And so when you add 0.01 moles of sodium hydroxide to that buffer solution, you end up with a pH of 4.83. Whereas, if you add that same 0.01 moles of sodium hydroxide to pure water, a liter of pure water, what would that pH result in? 0.01 moles, that doesn't really seem like much. It's a hundredth of moles. It's not really a large amount. How would I even calculate it? Well, let's see. In order to find the pH, I need to know what. pH is based off of what? And what's the H and pH from? Okay, it's from an acid. So in this case, I'm putting in a base. So in this case, the only acid that's in there is what was already in water now. So rather than actually getting pH directly from a hydronium concentration, I can't get it from pH, but I'm going to get it from the other side of that, which is what? pOH. Yeah, that's what I'm going to get it from pOH. So in order to do pOH, right, this is what I'm saying. I want pH, but I don't really have any H because this is a base. So here's what my plan is going to be. I'm going to do pOH, and I know that to get, if I'll just subtract that from 14, it'll give me my pH. And of course, to get pOH, then I need the OH concentration. So how can I get the OH concentration? From the information given. 0.01 moles of sodium hydroxide put into a liter of pure water. What's the concentration of the OH going to be? Yeah, it really is. Okay, it's going to be 0.01 molar. Because molarity, by definition, is moles over liters. And I have 0.01 moles of sodium hydroxide, which means I have 0.01 moles of hydroxide. I know you're like, it can't be that easy. And really, that's really all I'm asking. Make sure you're driving in the right direction. Liters, 1 liter, so that's nice and simple math. So yeah, that's where my 0.01 comes from. What if that was calcium hydroxide? What would my OH concentration be? What would it be? 2 times, which is okay. 0.02. Yeah, just check. Okay. So 0.02. Awesome. So now that I know my OH is 0.01 molar, because that's sodium hydroxide. What's my pOH? Make it even easier for you. This is something you can do in your head, right? This is 10 to the minus 2, 0.01. Okay. So, if it's 0.01, which is 10 to the minus 2, then pOH is 2. And if pOH is 2, then pH is how much? 12. Now, pure water, as you told me a while ago, started at 7. And when I put 0.01 moles of sodium hydroxide into a liter of pure water, the pH goes from 7 to 12. It goes up about 5 times. Whereas if I put that same amount of sodium hydroxide, that base, into this buffer, the pH went up by, started at 4.75, and then went up to this. So we do my math right? The difference went up by 0.08 as compared to going up by 5. So a buffer does resist changes in pH. For the same amount of hydroxide put into pure water versus put into this buffer solution, the change in the pH is different. Now, it's not really fair to compare 12 to 4.83. That's not the correct comparison to make. The correct comparison to make is pH before versus pH after. pH change. So again, the pH change for the water was 5. The pH change for the buffer was 0.08. Say that again, because I didn't think I heard that right.
The buffer doesn't resist as much.
The buffer doesn't resist as much. That's not the way I would say it. The buffer does resist. It resisted more. Resist means to avoid.
But okay, it doesn't change though. It
The
changes
buffer
more
has a
with
small
water.
chain, so that's a bigger resistance.
Yeah, so with the water, there's
The
less
water, there
resistance.
is less
Yeah,
resistance.
that's what I meant.
Okay, I thought that's probably what you meant, but that's not what I heard. But yes, so water has basically no resistance. Pure water has no resistance. So the hydroxide is in total complete control, and it's going to do what it's going to do. The water. Water can't resist. So the buffer has a greater resistance to a change in pH than the pure water. The pure water has less resistance. The pH of the water changes more. The pH of the buffer changes less. So if something's resistant, that means it's hard to move it. Right? You get all that resistance. It's hard to move. It's hard to move a buffer from 4.75 because that's the starting pH. We didn't do that calculation in this context, so we did it earlier. And even if we didn't do it, you didn't need to do a calculation because that's a magic spot for a buffer, right? When you have exactly equal amounts of weak acid and its own conjugate base, then you know the pH of that solution is Ka for that weak acid. So that's one of those special locations. One of those special locations that we took advantage of in the lab work that we were doing. When you drew that line at 2.5 drops on a graph and saw what the pH was, those 2.5 drops was a special location in titration.
So that's why they use right here.
Yes, I know the pKa because I can look up the Ka in a table. And then I just take the negative log of it. Once I have the pKa, I think that Henderson Hospital offers a much quicker calculation. So that's why I use Henderson Hospital. In order to do it, I do have to have the pKa. But that comes from the actual Ka value, which is something I can look up and always give it to you. Other comments? Thoughts? Questions?
What are you really measuring?
It's the change in pH that's valuable. So to know that this buffer started at 4.75, when I added that amount of base, it went up. So that's what base do, it increased pH. But it only went up by 0.08. And I can see that because I know it started at 4.75 and now it's at 4.82. So I can go get that number and see that it didn't change by much. Whereas water starts at pH 7, pure water does. And when I put that same amount of base into pure water, I get a pH all the way up to 12. So it went from 7 up to 12. So much larger change.
So that's what I was asking earlier. So does that
Okay.
mean that the base, or not the base, but the buffer is not as strong in the water? Because the point of buffer is to keep the pH maybe at the same level that it was. So it changed more with the water. The pH changed
Yes,
more.
it did.
So it had the buffer for that for the
No.
water.
No, and again,
It isn't.
it's my focus. If I want to travel a long distance and I want to get somewhere, I don't want resistance. if I don't want to move, then I like it. The purpose of the buffer is to have it. The purpose of the buffer is not to let the pH.
Right, right. That's one, so with the first example, it didn't move that much.
Yes,
The
it did
pH,
not.
But the second example with the water, it did move more.
It did.
So does that mean that the buffer was stronger when you're in situations, since it moved more with the
I think my problem is those words stronger and weaker.
Okay.
And it comes back to when I tried to use the word stronger when I was talking about a weak base instead of strong weak base or
Like
weak
you
weak
say
base.
it's more.
So those terms tend to have meanings. From our viewpoint, because we want peace, not change, and I would say, use those words, the buffer is stronger at maintaining pH.
On the left.
Those are both the same. There's no buffer on the right.
I'm confused. Okay, what was the point of doing the second problem here?
The second half, the one on the right, is where you don't have the buffer.
Okay, so it's just showing it, okay, that makes more sense. What is the buffer in the first one?
What is the buffer?
Yeah,
It's the combination of acetic acid and sodium acetate.
okay.
So you have those two components on the left, and you don't have them on the right.
Gotcha, and then the second one is the NaOH and water.
Yeah, so here's the picture. Let's see if I can do it this way. So I've got a container that's got 1 liter of water on the right. On the left, I have a container that also has 1 liter of water. So at the moment, they're both the same. What I'm going to do to the container on the left is I'm going to put in some acetic acid and some sodium acetate. And it doesn't matter whether it's acetate or fluoride or what it is. That doesn't really matter. It's the buffer, as long as I've got a weak acid and its own conjugate. So I'm going to take a weak acid and conjugate, and I'm going to put it in there. But I'm not going to put it over there. Once I put this into here, then it's going to do stuff with the pH. In fact, because of the amounts that I chose, it's going to put the pH of this at 4.75. The pH of that water is still 7. pH of this starts at 7. pH of this starts at 4.75. Now, if I'm trying to keep the pH as close to the starting point as possible, my buffer is going to help me keep that. But the water on the right has nothing with it to help it keep the pH at 7. So now I'm going to come in and I'm going to add 0.01 moles of sodium hydroxide. In goes 0.01 moles of a base. And of course that base is going to change the pH of the solution.
That's what OH.
I'm going to do the same thing here. I'm going to put in 0.01 moles of sodium hydroxide. Okay. And so what happens on the left is the pH goes up. It only goes up by 0.08. And the pH on the right is going to go up because, again, a base is going to make the pH go up. You've got no control over that. That's what base is. In fact, that's our definition. If you put something in the water and the pH goes up, you've just added a base. No matter what it was, you've just added a base. That's what they do. Here, it goes from 7 to 12. And from here, it goes from 4.75 to almost 4.82.
We're just showing how buffer works. Okay.
Yeah, it's a comparison of having that buffer as opposed to on the right not having that. In fact, well, yeah,
I get it now.
if I came over here and I put 0.01 moles of sodium chloride into here, it wouldn't change a thing. If I put 0.01 moles of sodium chloride and hydrochloric acid, so there's a strong acid and its conjugate base. And so if I put these two into here, the pH would not be 7 anymore. I could calculate what the pH would be. That would also not be above. And when I added that base, the pH would move a large amount. It's much larger than it does with the solution on the left.
But is there an adjustment?
That's not a buffer. Sodium chloride and hydrochloric acid is not a buffer. It's an acid. That's a conjugate base of that acid. It's not a weak acid and a conjugate base. That's a strong acid. That's a conjugate base. That doesn't make a buffer. Okay? Acetate.
The buffer, the equation for the buffer is you add the distilled water. So you're not actually really adding both of those into the water, are you?
Yes. What do you mean the equation?
The equation for the buffer. I think buffer.
Oh, here?
Yeah. So I'm buffer.
This is an equilibrium. What an equilibrium means, I know how we normally look at an equation. Normally we look at an equation and we see what's on the left, and we expect it to change into what's on the right. And that's the way chemical equations tend to operate. But in equilibrium, that's not the case. Not only does this change into what's on the right changes back into what's on the left. So the reality is that when you have an equilibrium, you have all four of those components in there at the same time. So if I take a container and all I put in is acetic acid, nothing else. Inside this container there will be the acetic acid that I just put in. But because of that equilibrium, it will produce some of this acid. So there will also be some acetate, and there will be some hydronium. And of course, there's already lots of water. So let me add that in. So in this container is all four of those all at the same time. All of them. Whether I physically step in and put some acetate in there or not, there's already acetate in there. Now, there's not much. Not much. Because the K is small. The K being small means that there's mostly what's on the left. All four are in there, but there's more of what's on the left than what's on the right. Now, for this situation, I don't just put that in here. I'm going to step in here and I'm going to put some more of this. It's right here. I'm going to put some more acetate than usually would be in there. So I'm going to pick that up. Some of that I put in there, equilibrium is going to shift to the left and add something to the right. But it can't take away everything that I just added. The equilibrium will not do that. So even though I add 0.1 moles of it, I'm still not going to have 0.1, but I'm going to have pretty close to that, maybe 0.099 or 0.098. I could do the calculation and see. But when I do that, add some more of this, there's still all four in here. So that's the thing you got to realize when you look at an equilibrium. You must recognize that all four of those are all in there at the same time. Whether I put any of the other one in there or not. So yeah, These two are on two different sides of that equilibrium. And it's actually why a buffer does what it does, because those two things are on opposite sides of the equilibrium. If for some reason they were both on the same side of the equilibrium, a buffer wouldn't function the way that it does. Other comments, thoughts? Okay. So let's go back to that buffer we were working with the other day. What if we had this buffer? And to this buffer, we're going to add 0.020 moles of hydrochloric acid. Okay. How we're going to do that, we won't worry ourselves with. So we're going to add 0.020 moles of hydrochloric acid. What's the pH of that buffer going to be next that we have done? Reminder, this is a two-step process, right? The first step involves what? Nice big S word. Okay, so wait on it. And then the second one is just equilibrium. And your choice here is either an ice diagram or the Henderson-Hausser one, whichever one you want. Or you can use either one of those. You must know what the starting equilibrium concentrations are. And it definitely is not 0.140 and 0.071. It's not going to be the starting concentrations for your equilibrium, your part 2. Because the first thing that has to happen is slow down.
So is this like HF plus it goes into the water? And is that do you know that? I guess I'm thinking something like that. That's when we added the acid.
Last time around we added hydroxide. And one of those went down and the other one went up.
I'm trying to think about it. Because you're adding that to water, right?
Adding what to what?
The HF to water.
Okay. Yeah, so I've got some water. And I'm going to put into here some HF. And I am also going to put into here some KF. And then I'm not even going to stop there. I'm going to add into here some HCl.
How do you write that?
Right. And here's what you've got to figure out. This HCl is going to react with one of those. You must figure out which one it is. Here's how you do it. Well, here's how you do that. HCl, acid or base. So this is an acid. HF, acid or base. That's an acid. KF, acid or base. Dedicated to salt, but the F part of it, the F minus, is the conjugate base of something. Base. So this added acid is a strong acid, this acid is a weak acid. Besides, they're two acids, so they're not going to react with each other. There's nothing they can do. They're both hydrogen donors, so what are they going to do? Nothing. They can't do anything. But this is a base, and that's an acid, and that's an acid. This acid and that base, they're just the conjugate base and acid of each other. What can they do? Nothing. Weak acid, its own conjugate base. But here's what we have. We have a strong acid. And over there we've got a base. So that's the reaction. That HCl is going to react with the KF. So we don't care about the K part of it because it's not, it's just a spectator. It's there, there's a spectator. And it's going to produce HF. This is an acid, that's a conjugate base. So what do acids do? They donate their hydrogens. So it's going to donate to that F minus to make HF. And then it's going to leave behind its own conjugate base. So yes, I expect you to be able to notice that that's the reaction that's going to happen. All of it. All of it. And once I know this, two things. One, chloride, once again, a spectator in this whole scene, so it doesn't matter to me. These are the key components right there. So when that HCl goes in there, what's going to happen to the amount of F minus compared to the original? It's going down. It's going to react with it and it's going to use it, so it's going down. And the HF over here on the right hand side, what's happening to it? It's going up. And again, this reaction is not an equilibrium. This is not an equilibrium reaction. Strong acids, strong bases don't participate in equilibrium. They drive to completion. The same kind of chemical reaction we've always expected. So, those 0.02 moles of HCl are going to reduce this fluoride by 0.02 moles. So it's not going to be 0.071 anymore. What's it going to be now? It's going to be 0.051. That's what the F minus, oops, put a bracket off of there. And HF? So it's always going to be the case. If one goes down, the other one is going up. So they're going to go in opposite directions. It's always the case. That we can rely on. Your biggest analysis here is going to be determining which one goes which way. Let's the HF go up, let's the HF go down. That's a huge plus. Somehow, some way, you've got to be able to put that in place. So when I add a strong acid, the conjugate base is going to go down, and the weak acid is going to go up. So that's what's going to happen. If I add hydroxide, which one of those two is it more likely to react with? 2. There's minus. And 1. Water doesn't matter because there's lots of water there already. It just joins the rest of the ground and goes on its merry way. So what's going to happen to the HF amount if I add hydroxide? It's going down. And the F minus? And that's what we saw in the previous example. When I added base to a buffer, it will increase the conjugate base and decrease the acid. Alright, so you finished the problem. We'll stop and take a break for that. So, what's the pH of this buffer going to be? And we're going to still, for the moment, play with that 3.15, which may or may not be wrong.